All right. Let's talk about test 3. 213 test 3. It's the standard arrangement, 25 multiple choice. I would look at the 2 tests that we went over on Tuesday, and then we did a test at the tutorial. Yeah. So take a look at the Tuesday lecture and the Friday tutorial. That will effectively go over everything that you need to know. I've been a little bit busy getting ready for the interview, so no new multiple choice were created. I will say that it is based on, you know how typically our multiple choice have 4 choices? This one will have 5, but the 5th one is usually either none of the above or something absurd, so you should be able to filter that one out really easy. Yeah, just those 2. There are a few other versions wandering around, and now that you have, I mean, if you really want to sit down and explore, there are test 3 reviews for 213 that have been done every semester for the last like 2 to 3 years. So you could sit down and go back and see all the versions of the test. I really don't think it would be all that useful. Efficient with your time is more accurate. So I would just go through those 2 versions. Appetizer, and then the 3 problems. Really, it all affects fluids, sounds, oscillations, and what do I know about Spring 213? I love you guys. So Spring 213 means boring tests. And by boring, I mean, I'm not really putting a lot of effort into it. Very conventional. And to some people, they go, well, I'm insulted by that. And you guys are like, oh, I know what that means. So it's not, I'm not doing extra tricky things. It's, you know there's an Atwood string. It is not that mass is not resting in water. So we're not doing that crazy one. It's continue. Shall we? I'm not gonna. I refuse to acknowledge that question. So let's just go with that. But the bucket of brains one, to speak about it, it's an Atwood string problem. The mass, the thing about the Atwood string and the bucket of brains problem, everybody thought the bucket of brains was just whacked out. But all it was the number of brains times the mass of a single brain was equal to the hanging mass. And that was it. That was the extra step that just flipped people out. And, well, actually, technically, that Atwood's brain machine thing was, you had a bucket, you had N brains in it, so the hanging mass was the mass of the bucket plus N times the mass of one brain. And all you had to do was solve for N. So substitute this into a standard Atwood string problem, boom, you got it. It's not that, it's just an extra layer of algebra. It's not that big of a deal. Probably Doppler shifting. And probably understand the roulette wheel problem. Understand typically you don't initially need the frequency of the source. All you have to do is you have to take one of the frequencies and divide by the other. and then solve for velocity. Me giving you effectively what's on the test, I expect the solutions to be written out in full. I don't want, because my professor says so, answer equals 42. I want the solution, so understand how to go through all the steps. Basically, the outward string and the Doppler shifting, I could ask for any of those variables, so be able to solve for any of that stuff.
I was wondering when I finally get all the numbers and everything, all the letters, like what A and B, does it matter order? Like I multiply fractions, like it is 4f squared L squared.
As long as it follows the standard rules of math. Multiply before you add, divide before you subtract.
I was just wondering if I had like f squared, like 4f squared, and so
No, no, it doesn't. It all depends on your preference on how to enter it in the calculator. The other stuff, there is a fluids problem. So be ready to use Bernoulli's equation, be ready to use buoyant force, be ready to deal with any of those standard fluids problems. And when I'm talking standard, I'm talking standard. So if I was studying, I would look at the review sessions first. I would then branch off to the tutorial videos second, and then I would look at the lectures third. The test reviews review the test, the tutorials are the solution sets to the problem sets, and then the, and then the lectures go over those, and I'm really going through everything. Just understand the basic ideas of how to get the stuff done. The multiple choice is standard, the problems are standard. It's a dull test. Appetizer, I'd probably say oscillations. Because remember what we did. We did fluids, we did oscillations, we did sound. If 1, 2, and 3 are fluid, strings, and Doppler shifting, I got nothing left. So in my bag of tricks, there's nothing left. So I would think oscillations, the typical something goes up and down 20 times in so many seconds. What's the mass? What's the spring constant? What's the length of the pendulum? It's not that thing. My general impression for writing the test, and once he leaves, then I'll give you all the answers for true. So you're gonna have to take one for the team. The number 7, the answer is B. Okay. I don't know. The let's see. My impression of the grades of the class, running slightly cold, as in running slightly below what I want them to be. If everybody had 90s, that would just mean excellent playtime, and I get to throw out some interesting problems. Because the grades are kind of, I would say they're about right after I'm probably going to give a 4-point correction to test 2. So the average of the class is just about right. So I didn't know applause was that easy. Okay, 5 points. Joy, no, so yes. No, 4. 4 total. I've decided for test 2, for 213, it's a 4-point total. I think there was one multiple choice where it was definitely botched, and then a second multiple choice where I was like, I get the point, and so might as well get it. Yeah, and in the end, it's like 4-point correction, 4-point curve makes no difference. It still boosts everybody's score by 4 points. So it's not that big of a deal. It is in the book, yes. And actually, do me a favor. Next week, come to me and say, did you write it in the book, and get me to show you? Otherwise, I'll... Yeah. For something like a big point shift on a test, I will not be offended if you only Only you. Don't have 30 people come to me and look for the book. Just you. Be sure to come to me and remind me in my office, and then I'll double check and I'll rewrite it again if necessary. It's a dull test. When you look at it, you go, oh, he took this from this, he took that from that, he took this from this. It's not anything special. 214, I made a few changes. 213 now. It's
So if we do the questions,
what? Huh?
if we do the questions that are on the test that are already out, we should be fine.
Yeah, I would say that. If you go around and you find, I mean, their copies, I'm opposite of a lot of professors who go, none of my copies of my test should ever be out in the wild. Everything is out there. I would say if you look at test 3 reviews for last fall, or even the fall before, you probably have seen the test. So it's not, it's there. You're going to look at, the moment you flip the page and look at the problems, you're going to go, well, of course. And then I'm going to cackle wildly. And so there it is. I can't tell you specifically, but it amuses you, apparently. So, yes, I was talking about her. All right. So short of me saying what's on the test, what else can I answer? What type of fluid problem? I'll let him pick. I talk to you all the time. What? What type of fluid problem? Which one? I don't have the test with me. I've literally just shown up from Columbus, long enough to change shirts. I didn't show up to my interview on this. That would be awesome. The helium one? Is it helium in water or helium in air? I'm too tired.
Yeah, that might be it. That voice.
This one? Okay. Helium is held down to the ground by a string. It's not moving, which means it's doing a lot. The sum of the vertical forces is equal to 0. Now, the tension they give you is 1,000 newtons. The volume is 700 cubic meters. The helium-filled sphere is held to the ground with a string. Given the values listed, what is the mass of the balloon? So we're looking for the mass of the shell itself. To do a force diagram, the buoyant force is up, the tension is down, the mass of the balloon times gravity is down, and the mass of the helium times gravity is down. Huh? What'd you say? Yeah, there's 4 factors. I thought you said fulcrum, and I was like, what? Now, technically, these two should be attached to this, both going down, but I just wanted to hold them out a little bit separately. All values will be given in terms of densities unless I ask for it or it's unnecessary. Density of helium that we use is 0.18 kilograms per cubic meter. Density of air, 1.3 kilograms per cubic meter. Gravity, we'll say, is 10. Sum of the forces is equal to 0. This means buoyant force minus mass of the balloon times gravity minus tension minus mass of helium times gravity. Mass of the balloon times gravity. Buoyant force becomes density of fluid replaced, volume, and gravity. The fluid displaces air. Minus balloon gravity moved over, minus tension. Now, minus mass of helium, I don't know what it is. But density is mass divided by volume. Just to keep things straight, rho, RHO, that's volume mass density, or we think of as standard density. Lambda is what? What's the difference between rho and lambda in the way that we use it? Lambda, correct, is linear. So whereas the units of rho are kilograms per cubic meter, excuse me, lambda is kilograms per meter. Know that those units are different. We are using air because what are we displacing? No, we're not displacing helium, we're displacing air. The problem, air is kind of written off to the side and it says balloon filled with helium on it. So we're using air. And the mass of the helium becomes density of helium times volume times gravity. Divide by gravity. Mass of the balloon, rho A V minus T over G minus rho HE V. Plug and chug. That's it. You got T, you got G, you got the densities, and you got volume. I divided both sides by G. Tomato, tomato. Yes. Buoyant force, remember, okay, what we need to clarify, definition of buoyant force. Excuse me, I'm still recovering from that cold. Buoyant force is rho VG. What's the rho? It's the density of the fluid displaced. If it's a bucket underwater, the fluid is water. If it's a balloon in the air, it's air. Doesn't matter if inside the balloon is helium, air, or water, the fluid being displaced by the balloon is still air. That's the fluid pushed out of the way. A helium-filled balloon in water, the density of the fluid displaced is water. It's whatever is displaced. The V is the volume of displacement. Typically, all of our volumes have been completely submerged. And I guess to give you a tip, I feel uncomfortable using partial submersion problems. These would be full submersion problems. There's only been one or two where we've done partials. So in that case, the volume of the balloon is the volume displaced. Yeah, well, a balloon underwater means the fluid displaces water. A balloon in the air, the fluid displaces air. Yes? You can tell me? Okay, what is it?
Okay, so the cylinder of the hole is shown below. How long will it take you to specify volume to come out the hole?
That was talked about in so you've got a bucket with a hole. What do I need to know about the hole?
So radius is 1 over the square root of the
We've done, I think we,
I just have a question. You don't know the velocity coming out of the hole. Sorry. You don't know the velocity of the water coming out of the hole. Do you use Bernoulli's equation to find the velocity?
Yes.
And then go back?
yeah, I'll do the setup for this. So, my least favorite equation is this. And this is really kind of an application of a little bit more, a better of a problem than, or it's a better problem than the shower curtain problem. But it illustrates the same type of setup. Let's look at a blown up portion of, so here's the hole. The velocity on that side of the hole is V. The velocity on this side, the water is coming in from all different directions. So you can safely say that the average velocity of the fluid just inside the hole is 0. So that makes that 0. The points that we're studying are, one is just inside, other one is just outside. Those cancel, they're at the same height. The key difference is that P2, which is out here, is standard atmospheric pressure. So it's PATM plus 1/2 rho V2 squared. Now P1 looks like a little bit of a cheat because it's almost like it reintroduces rho GH. But P1 is equal to PATM plus rho GH. The way that I have H set up, H is not H1. H1 is the altitude at that point. This H is the depth underneath the surface. Those cancel, and I'm left with rho GH, who's 1/2 rho V squared, and you can now solve for V.
Why would we do, instead of replacing P1, that, why would we put force over area and change it to the mass over the area? And then
You could, but what we have shown, yes, pressure is force over area. But what we showed is there was a particular homework problem. It was the steel cylinder. And I asked about the pressure at the bottom of the cylinder. And what we showed is you can just straight up say that the pressure at the bottom is merely the depth of whatever substance is on top of it. The geometric arrangement doesn't matter. All that matters is what's sitting on top of it. And there is a derivation. I would look at the tutorial for problem set 7, because I think that's the one where we did it.
And then you did give a velocity of the water coming out. You just use flow continuity, right?
Yeah. Oh, one of the things that the equation of continuity is A1 V1 is equal to A2 V2. And I call this flow. That the flow rate, the amount of volume per unit time, is constant. And volume is that flow times time. You multiply the flow by the time, you can get the volume. And so if I say, how long does it take for 10,000 cubic meters to shoot out, and you know that it's 10 cubic meters per second, you can get the time out of it. Yeah. So, that's good. I'll give another answer now that she's leaving. Yes.
Can you do Atlas machinery solve for
L1? Okay. Now it's similar to this, but instead of asking for the mass of the string, I'm asking for L1. Oh. You know what? I may not end up asking for L1. The problem, don't worry about that. Because the problem is with the setup of L1 is sitting in two different places. One that it's in a sum and the other one in the divisor. No, don't, I can tell you no, don't worry about that. Solving for L2 and everything else in that particular problem is doable. L1 may be solvable quadratically, but since we don't do quadratic equations in here, I don't bother. Yes? Can I do the Doppler? Okay. We'll do it again. We did one. I have the frequency that I hear towards and away. What is the speed of the motorcycle? What is the length of the Pied Piper's pipe? It's opened at both ends and it's at its fundamental frequency. So it is definitely a hybrid problem for test 3. The frequency towards and away, we're dealing with a moving source. So it's F over 1 minus V over Vs, F over 1 plus V over Vs. F's cancel, and I'm left with 1 plus V over Vs, 1 minus V over Vs. And so we have this. Cross multiply. We get this, distribute. Move stuff over. Factor. Solve for V. And so that'll give you a number. 350, 500, 200, 500 plus 200. So that's 300 over 700, 3/7 of 350. 150 meters per second? I want to say. 300 over 700 is 3/7. Yeah, so it should be 150.
Why did it switch on the third part? It says FA, B or BS, TB or BS. Why did it switch like
This is in the denominator of the denominator. So what's 1 over 1/2? 2. The denominator of the denominator comes up to the numerator. Now that you have the velocity, I can get the core frequency. I'll take one of these. Let's save towards. F over 1 minus V over Vs. F. Ft 1 minus V over Vs. Ft 500. 1 minus 150 over 350. 1 minus 3/7 is 4/7. 4 times 500 is 2,000. 2,000 divided by 7. Whatever that is. Now that you've got the frequency, it's a pipe. So this is NV over 2L. I'm looking for L. So this is NV over 2F. It's at its fundamental frequency. It's 1. This V is not the velocity of the object. It's the velocity of sound and air. So this becomes 350. And then this is 2 times whatever 2,000 divided by 7 is. And then you got it. Yes. If you used F away equals F over 1 plus blah, you would still get 2,000 over 7. It doesn't matter. It's the same thing. Yeah, and that's it for number 3. Yes. What? In the problem, I said it's at its fundamental frequency. Therefore, n equals 1. Now, 1 and 2. Yes. I would say it's a valid situation. I would kind of would think not. I'm not emotionally prepared to deal with answering that tonight. But I'm dimly seeing what's on the test, and you got enough to study. That's not one of them. There is a fluids, there is a sound, there is a Doppler shift, there is oscillations. I mean, that I'm not divulging anything. To just say there's no mixture in the balloon, if it's there, is not a big. I'm not losing much. Yes. So I said that on Earth, a simple pendulum oscillated how many times? 4 times. In 45 seconds? 4 pi seconds, not square root of 4 pi? All right. So if that is given, on Earth, I know that G is equal to 10. Therefore, period is 2 pi square root of L over G. Now, what do I know about the relationship between period, time, and total time? That n times period is total time. So n times 2 pi L over G is equal to T. I know what G is, that's 10. I know what N is, that's 4. I know what time is, that's 4 pi. Solve for L is probably what I'm looking for. So I'd square it. N squared 4 pi squared L over G T squared. Look for L. L T squared G over 4 pi squared N squared. And then you plug in stuff. T is 4 pi, T squared is 16 pi squared. G is 10 over 4 pi squared. N is 4. And this is why when you look at this and you go, the time is 4 pi seconds? That's so freaky. Why would he ever pick that? Because Dr. Eschenberg is as lazy as you. What's 16? 4 times 4. Answer. I don't even have to use a calculator for this. It's 10. It's got to be 10. So, yes. If I was looking for the period, I could say it is T over N. I know what it means. I don't think it's that. I don't think I would test anything along those lines. I'm not sure. I think you're kind of. I think you're overthinking this. I think. It's really just get it to this part and then solve for whatever you need, and then that's it. Yeah, I think what you're doing is you're arguing hypotheticals, and if you understand it in general, everything should be fine. Yes. All right, fine, sue me. That's squared, that cancels with that, so now it's 10 over 4. Answer's 2.5. Oh darn, it's that much more complex. But you are correct, you fixed it. So, a imaginary bonus point for you. What else? Yes. You would never go wrong with keeping all the answers in kilograms. Make sure, I would say for that particular, what are the units of all the densities? Kilograms per cubic meter. So whenever you get anything, you will never go wrong with using a System International unit, a metric unit, meter. If you, if I say convert to grams, then convert it. I would say my understanding of the test is there's nothing in there that asks for anything other than standard units. So I wouldn't keep it conventional. Yeah, that's fine. It should, the answer that you get out of the solution that I gave you should be in kilograms. Yes. Of a what? I just did it. The roulette wheel problem is this.
So then, whenever you go on a different test, you are good with that ratio.
It could be, yeah. I would. Hold on. It's been a long day. The roulette wheel problem, in my opinion, is probably a classification, a general classification of problems. The roulette wheel problem, remember what I said in class, I will not require you to understand what theta naught is for any other problem other than the one roulette wheel problem that I did in class. So you're never going to have to understand theta naught. But the roulette wheel problem gives you a solution to how to solve Doppler shifting when the source frequency is not given. A lot of people freak out about the frequency of the source not being given, and your head is excellent at blocking your other head, at the head. So if it's a motorcycle driving by and you hear two frequencies, that's a roulette wheel problem. You've got the frequency as it's coming towards and away. If you're in a train and there's a whistle at the train stop and you go by and you hear two sounds, you do the same thing, but now you're using the moving observer equations, towards and away. Is it towards divided by away or away divided by towards? Yes. Either one will give you the correct answer. It doesn't matter. So this is real. This could be done for anything. I'm just showing you the general solution. Yes. I gotta think of one. I got it. I won't do that one. I don't want to do that one. Professor's cranky. Professor needs a beer. I checked the vending machines. There's no beer in the vending machines. That would be epic. Spring pendulum, 20 seconds, oscillates 4 times on Earth. This experiment will all occur on Earth. You bring the spring pendulum to a stop. What is X? What is the difference between the rest position and its straightened position if that hanging mass is 4 kilograms? These numbers are just pulled randomly. I don't know if they're going to be nice or not. So the period is 2 pi m over k. The total time is n times period, so t is equal to n 2 pi m over k. Now, a hanging spring, Hooke's law, the force pulls up, gravity force of gravity pulls down. When I say you bring it to a stop, that thing is not moving, so the sum of the forces is 0. So the sum of the forces vertically is equal to 0, which is equal to Fk minus Fg. So Fg is equal to Fk, so Mg is equal to Kx. So the hanging mass and gravity and the spring constant and X, and I got all this stuff. Now the question was, how far is this thing hanging from its normal rest position with no mass on it? I.e., what is X? I know mass, I know gravity, but I don't know K, so I'm going to have to solve for K here, plug it in there. T squared 4 pi squared n squared m over K, so K is 4 pi squared n squared m over t squared. Now the thing about this is, like I've said, like I showed in the test review lecture on Tuesday, is mg equals 4 pi squared n squared mx over t squared. The m's cancel. So g t squared 4 pi squared n squared is equal to x. Plug and chug. That's all you gotta do. Do you need a number? Well, let's find out. 10, 20 squared. That's 400 times 10 is 4,000. Divide by 4, now we're at 1,000. Divide by pi squared, I have no idea what that is. And then that's 4 squared. Whatever that is, I don't know. Anything else? We could probably go for another 5 minutes and then I'm done. If not, we're done. Because I need a break. Because after I spend a day interviewing for a job about physics, I love to sit down, teach physics, take a break, and teach more physics. So, teaching the 214s in about 10 minutes. Oh, and they're horrible. 214s, they're not in right now. They're horrible, horrible people. They even smell bad. Huh? Yes. Yes. That's a valid problem. That's really when if that was on the test and you look at it, there should be, I'm not saying it's a little bit gross, there should be a little bit of drool. You should get all like, oh, I'm excited, because it's a plug-in chugger's dream. It's equation of continuity, A1 V1 equals A2 V2. I give you everything, solve for V2, and then P1 plus rho G H1 plus 1/2 rho V1 squared equals P2 rho G H2 plus 1/2 rho V2 squared. And then everything is given. The one thing that it does test for that you should be warned about is be very careful about what unit I'm asking for. Typically, the pressures that I give are in atmospheres. The resultant of these 4 factors are in newtons per meter squared. You need to be able to convert those into atmospheres or atmospheres into newtons per meter squared. That conversion factor will be given. I mean, it's just given if the problem's used or not. 1.013 times 10 to the 5th, which normal physicists don't know. They just look it up, but I've said it 50 billion times. So, that's a good, but what you asked for is a very good question. Examples like this have been done in your lecture notes. In the lecture notes and in the tutorial. So I would definitely look at that. And, no, I've just thought of an evil problem, but that's definitely not going to be on the test. The problem that I would give that would be fun is you have a balloon, it's floating in the air, you pluck the string, it's 4,000 hertz at its second harmonic. What's the volume of the balloon? So, I know, right? But that's not going to be on the test, so I wouldn't worry about it. All right, I think we're done. All right, any last minute questions? Going once, everybody's standing up. We're done. Done. Go home. Study hard.